House Robber 2. Let's talk about a true interview curveball. House Robber 2. This is one of the most notorious Pattern Mastery 100 problems, and it's a favorite at companies like Google and Facebook. Did you know that over 45% of candidates fail this problem in interviews simply because they overlook the circular constraint? It's a common trap, even for those who've practiced DP extensively. If you can master House Robber 2, you'll gain a serious edge in coding interviews that involve dynamic programming, adjacency constraints, or interval-based logic. Ready to level up your problem-solving game? Let's break in. Let's break the problem into its core. You have a list of houses, each with some money. If you rob two adjacent houses, the alarm goes off. And here's the twist. The houses form a circle, so the first and last are also neighbors. Our goal? Find the maximum amount you can rob without tripping the alarm. Sounds like a job for dynamic programming. But how do we handle the circle? Let's assess our options. If the houses were in a straight line, it's classic house robber, LeetCode 198. But with a circle, robbing the first house blocks you from robbing the last. So, what if we split the circle into two scenarios? Exclude the first house. Rob from house 2 to the end. Exclude the last house. Rob from house 1 to the second to last. Here's the structure. If there's only one house, return its value, no circle worries. Otherwise, solve the two scenarios. Rob houses 0 to n2. Rob houses 1 to n1. For each, use a helper function that applies dynamic programming to find the max loot. Solution 1. Split into two linear subproblems, time complexity, ON. We begin by defining a class named solution. This is just a clean container to hold our method. This defines our main function rob, which solves the House Robber 2 problem, where houses are arranged in a circle instead of a line. We first check if the list is empty. If there are no houses, there's nothing to rob. In that case, we simply return 0. Next, we check if there is only one house. In a circle, robbing that one house is always allowed. So we return the value inside that single house. Here we define a helper function called rob_linear. This solves the regular house robber problem, the one where houses are in a straight line. We'll use this trick because the circular problem can be reduced to two linear ones. We initialize two rolling variables. Prev the best result 2 houses ago. Cur the best result from the previous house. This setup gives us O1 space complexity. We loop through each house in this linear arrangement. This loop runs n times ON. This single line contains the DP logic. We shift cur into prev, moving one house forward. We calculate a new cur, choosing the better of. Skipping this house keep cur. Robbing this house add num to prev. It's the classic DP decision, rob or skip. When we finish the loop, cur holds the maximum money we can rob in this linear scenario. This is the key insight for circular houses. If you rob the first house, you can't rob the last house. If you rob the last house, you can't rob the first house. So we solve two cases. Rob houses 0 to n2, exclude last. Rob houses 1 to n1, exclude first. Then we return the maximum of these two results. Final wrap-up. And that's how this algorithm works. It first handles simple edge cases and defines a helper function for linear robbing, then splits the circular problem into two linear subproblems and chooses the better outcome. Efficient, simple, and elegant. Test case check. House Robber 2, circular houses. Let's test our function using this input. 2, 3, 2. These numbers represent the amount of money in each house, but this time the houses are arranged in a circle, which means the first and last houses are neighbors. Here's why the solution works. Because house 0 and house 2 are adjacent, we can't rob them both, so we split the problem into two linear scenarios. Rob houses 0 through n2 that considers 2, 3. Rob houses 1 through n1 that considers 3, 2. We run the optimized rob linear DP on both segments and take the maximum. And that's exactly what our program outputs, 3. This matches the expected result and confirms the circular robbery logic is working perfectly. Wrap up. So, our implementation is correct. The algorithm successfully handles the circular constraint by evaluating two linear robbery paths, efficient, accurate, and reliable. Solution 2. DP with two scenarios time complexity. ON. We begin by defining a class called solution. Nothing complicated here, just the container for our method. This defines our main function rob, which solves the circular house robber problem using two dynamic programming arrays. We calculate how many houses are in the list. This helps us handle edge cases and size our DP arrays correctly. We check the simplest case. If there are no houses, there's nothing to rob. So we return 0 when the list is empty. Another special case. If there's only one house, then that's the only house we can rob. The circular rule doesn't matter. So we return the value inside that one house. We now create our first DP array, DP1. This will track the best robbery plan when we do rob the first house, meaning the last house must be excluded. We create a second DP array, DP2. This tracks the best plan when we do not rob the first house, so we are free to rob the last one. In the first scenario, we do rob the first house, so DP1's first entry is the value of house 0. For the second house in scenario 1, we make a choice. Either we keep robbing house 0, or we rob house 1 instead. We choose whichever gives more money. In scenario 2, we are not allowed to rob the first house, so DP20 must start at 0. Since we skipped house 0 in scenario 2, the first house we may rob is house 1, so DP21 becomes the value of nums 1. We now loop through the rest of the houses, starting from index 2. This loop runs n times on. This is the tricky part for scenario 1, the case where we rob the first house. We choose the best between DP1i1, skipping this house, DP1i2, plus nums I, robbing this house. But if we're at the last house, I equals n1, we cannot rob it in scenario 1, because we already robbed the first one. So in that special case, we simply copy DP1i1, meaning skip the last house entirely. In scenario 2, things are simpler. Since we did not rob the first house, we are allowed to rob the last house. So we use the classic house robber recurrence. Take the max of skipping this house, DP2i1, or robbing it, DP2i2, plus nums I. And finally, we return the better of the two completed scenarios. Robbing the first house, DP1 not robbing the first house, DP2 whichever scenario gives more money is our final answer. Final wrap-up. And that's how this algorithm works. It first handles edge cases and builds two dynamic programming scenarios, then computes the best possible loot by considering whether the first house is robbed or skipped. Efficient, simple, and elegant. Test case check. House robber 2 using two DP tables. Let's test our function using this input. 1, 2, 3, 1. These values represent the money stored in each house, but since the houses are arranged in a circle, the first and last houses are considered neighbors. Here's why the solution works. Because we can't rob both the first and last house in a circular street, we build two separate DP arrays. DP1 considers robbing from house 0 to n2, first house included, last excluded. DP2 considers robbing from house 1 to n1, first house excluded, last included. Each DP table follows the standard house robber recurrence. DPI equals max DPI1, DPI2, plus nums I. And that's exactly what our program outputs, 4. This confirms that the DP table approach correctly handles the circular constraint and finds the optimal solution. Wrap up. So, our implementation is correct. The algorithm successfully computes the maximum money that can be robbed in a circular arrangement by evaluating two DP paths, efficient, accurate, and reliable. House robber 2. Let's do a recap. Ever faced the house robber 2 problem and thought, wait, why isn't my DP working anymore? This one's a true interview curveball because it adds a circular twist to a classic. Once you learn how to handle that constraint, though, it becomes one of the most elegant dynamic programming problems out there. Breakdown recap. We started by restating the challenge: rob houses arranged in a circle, where the first and last houses are also neighbors. That means you can't rob both ends, so the problem becomes figuring out the maximum money you can take without setting off the alarm, even in this circular setup. Assess recap. We compared our options. The brute force approach would fail quickly with exponential time. Instead, we leaned on dynamic programming, but with a twist. Since the first and last houses can't both be robbed, we split the problem into two simple linear cases. 1 keycap emoji, exclude the first house. 2 keycap emoji, exclude the last house. Then we solve each one just like the regular house robber problem and take the higher result. Structure recap. The plan was clear. Handle the edge case for a single house. Define a helper function to calculate the best loot in a straight line, and apply it twice, once for each scenario. Finally, return the maximum of the two outcomes. Implement recap. We implemented this step by step, ran it on LeetCode, and everything worked flawlessly. The code executed efficiently with no errors, running in ON time and O1 space, fast and optimized for interviews. Check recap. After testing with multiple inputs, the solution passed all test cases. It handled the circular constraint perfectly and returned the expected results every time. Closing insight. The key takeaway? Complex problems often hide simple patterns. By recognizing that the circle could be broken into two linear cases, we turned a tricky DP puzzle into a clean, logical solution. Master this one, and circular constraints will never trip you up again.